Good evening. Welcome to the second lecture for the chapter Complex Numbers and Quadratic Equations from class 11 Mathematics. So we had started with complex numbers and then we saw we revised a little bit on the different number systems and what exactly are real numbers and imaginary numbers. So just a quick recap. So we defined an imaginary unit I such that I gives you the square root of -1. Okay, since it's difficult to find the square root of negative numbers, this unit was introduced. So that means I square is equals to -1. Okay, so this was the imaginary unit. And suffixing this imaginary unit with any real number. Okay, so maybe 3i or 5i. Okay, so these then become the imaginary numbers. Okay, so these are imaginary numbers with a real number coefficient. So these were imaginary numbers. So then we went on to see what are complex numbers. Okay, so complex numbers can be written in the form of Z. Z is a complex number. So Z is equals to A plus BI or IB, in whichever form we write. Okay, so A is the real part of the complex number and B is the imaginary part of the complex number. Okay, so complex numbers are made up of both real and imaginary numbers. So this is something that we saw. We tried to express a few, expressions, simplify them and write them in this form. We also saw how we can find different values of various variables when they are a part of the complex numbers. Okay, and one important aspect that we saw was if two complex numbers are said to be equal if their real parts, okay, real part of Z1 is equals to real part of Z2, and also if their imaginary parts are equal. So when we are considering, so the real part of the complex number is A and the imaginary part is actually BI. So B is the real number coefficient of the imaginary part. Okay, so this is something we had done in the previous lecture. Now we will move on to the different algebraic operations that can be done or that is applied on complex numbers. So when we are solving equations dealing with complex numbers, there are a few rules that the operators have to follow. Okay, so if you are adding two complex numbers, there are a few rules that they have to follow. They have to satisfy some properties. Similarly, for the other operations, we will see if the set of rules that are being applied on one operation is also satisfied when we are changing our operation. Okay, so first we will go into the addition of two complex numbers. So over here, as we can see, so Z1 is equals to A plus IB and Z2 is equals to C plus ID. Okay, so the sum, always the sum of two complex numbers. Okay, so Z1, as we have already seen, is A plus IB. So the real part, okay, of the sum of the complex numbers. Okay, so it has to be the real part would be the summation of the sum of the real parts. Over here, as you can see, A plus C. Okay, and the imaginary parts have to be added together. Okay, so you cannot add the real part of Z1 with the imaginary part of the Z2. Okay, so that is not how you can calculate. So this has to be the way that you do. So the real part of Z1 is added to the real part of Z2, and the imaginary part of the Z1 is added to the imaginary part of the Z2. Okay, so for example, if we take Z1 and Z2 over here, so Z1 plus Z2 will be equal to 8 minus 3i plus 3 minus I. Okay, so you bring the real parts to one side, 8 plus 3. Okay, you keep the addition sign outside since we are adding. Okay, sorry. So then you have minus 3 and minus 1 I. Okay, so what you are left with 11 plus minus 4 I. So this is 11 minus 4 I. Okay, so this is how you add. And then if we want to see what is Z3 plus Z4, now you can see for Z4, there is only a real part. Okay, so if we just calculate straight away, so since there is no imaginary part, so this remains and only the real parts get added. So this is 12 plus 4i. Okay, so this is the addition operation that is done on complex numbers. Now, the some properties that we that it has to satisfy for the addition to be valid. So, as you saw, if we take the Z1 plus Z2, okay, so your Z1 was 8 minus 3i, okay, and adding your Z2, so that was 3 minus 5. Okay, in this, the result that we got, okay, over here, this was the result that we got, so that was 11 minus 4i. As you can see, this itself is in the form of a complex number. Okay, so hence, with addition, we can see that the closure law applies when we are adding two complex numbers. So that the sum of two complex numbers is a complex number. Okay, now we will see another law, that is a commutative law. So as per the commutative law, it is stated that Z1 plus Z2 is equal to Z2 plus Z1. Okay, so if we want to see if this actually holds true, we take Z1 plus Z2. Okay, so we have already got the answer for that. Now, if we reverse the order as is on the RHS part, okay, so you have Z2 plus Z1. So your Z2 is 3 minus I, and then you add 8 minus 3i. Okay, if you again separate the real parts and the imaginary parts, so you're again left with 11 minus 4i. Okay, so therefore, the commutative law also holds good when we are adding two complex numbers. Okay. Now we will see the associative law. Okay, so as per the associative law, if you are given three complex numbers, okay, so we have Z1, Z2, and Z3. So Z1, Z2, Z3 says that the associative law states that Z1 plus Z2 plus Z3 is equals to Z1 plus Z2 plus Z3. Okay, so this means the sum of the first two numbers plus the sum of, when it is added to the third complex number will be equal to whether you add the second and the third number first and then the second and the third number at first, and then you add the result with the first complex number. Okay, so this is the associative law that that also holds true when we are adding. So for example, we will see an example over here, since like there is not much space over here. We can see, okay, for associative law. Okay, so we will try to see if it holds good when we are taking an example. Okay, Z3 and Z1 plus Z2 plus Z3. Okay, so I will just write the numbers that we were using in the previous examples. Z2 is equals to 3 minus I, and Z3 was 6 plus 4I. Okay, 6 plus 4I. Okay, so first let's take the LHS part. So Z1 plus Z2, okay, plus Z3. So you can, so this first you can, put in the values that are being asked, that are being provided, plus 6 plus 4I. Okay, so this is the LHS part. So this we have already seen. Okay, so that is 11 minus 4I, okay, plus 6 plus 4I. Then similarly, again, if you take the, we add the real parts and we subtract the imaginary parts. So we will see that 11 plus 6, okay, 17. And since this is minus 4I and plus 4I, so we will be getting 0. Okay, so the answer is 17 for the LHS. Now let's see if we get the same answer if we, solve for the RHS. So as for RHS, we have Z1 plus Z2 plus Z3. Okay, so we will first solve the Z2 plus Z3 as we have in the brackets. So we write Z1 outside. Okay, so Z2 is 3 minus I plus 6 plus 4I. Okay, so what do we get in that? 8 minus 3I plus, again, take the real parts first and you add them up. So that is, sorry, 9. Okay, so this is 9 and you have minus I plus 4I. So that would be plus 3I. Okay, and then again, we see that the real numbers, if we add them up, it will be 17. And if we add the imaginary numbers, it will be plus 0. So what we are left with is 7, and that is your RHS. So you can see that the LHS is equals to RHS. So the associative law holds good and it is satisfied when we are trying to add two complex numbers. Okay, over here we have taken three complex numbers. So this is the associative law. Okay, so we have done the example. I'll just mention example on the next page. Okay, so now we will see that there is a certain property that exists that is called the additive identity. Okay, so additive. So anything, suppose you have a complex number that is 0 plus I0. Okay, suppose there is no imaginary part, there is no real part. Okay, so a complex number can be 0. Okay, so as we had seen in this example over here. Okay, so since there is, you can write this as I, okay, but any which way this part will become 0. Okay, so you have this is called the additive identity or zero complex number. Okay, so that exists. It can help us to, if suppose you have one Okay, Z1 is equals to 8 minus 3i. Okay, and your Z2 is equals to 0. So what you get Z as Z1 plus Z2. Okay, so what you get is 3i. Since this can be considered as a complex number, if you even add it, what you're left with is 3i. Okay, so if you add anything to, if anything comes up to be 0, then what you will get is the only the remaining complex number that was used to add it up. Okay, so this is the additive identity. The last one, the last property that exists when we are doing the algebra of complex numbers is the additive inverse. Okay, so we had additive identity or zero complex number previously. Now we have the additive inverse. Okay, so what is an inverse? So if you have z is equals to a plus ib. Okay, so for example, we take z is equals to 4 plus 5i. Okay, so if you add, if you change the signs of the components or the coefficients of the real and the imaginary parts. So suppose you have z1. Okay, if you take, so if you make you add the minus sign to 4 as well as 5, so and you keep this operator between the two parts. Okay, suppose this is what you have got when you add. Okay, this is minus 5. So what Z1 is actually, it can be denoted as negative of Z. Okay, so if you actually change the sign of the real parts and the imaginary parts, keeping the sum operator in between, okay, for in a complex number, what you get is, this is called your additive inverse. Okay, or negative of z. We will see how this comes in effect when we try to do the other operators. Okay, so if you have, say, as we had taken z1 is equals to 8 minus 3i. Okay, so when we want to get the additive inverse of z1, we will get it as minus 8. Okay, plus 3i. Okay, so you change the signs of both of the coefficients. If you actually change this as 8 plus minus 3i. Okay, so if you separate out the signs for the operator and the coefficient of the imaginary part, okay, so what then you can change it, okay, to negative 8, and then you get plus 3i. So since we did the algebra to understand the addition of two complex numbers, now we will see what would happen if we have the if you want to find the difference between two complex numbers. Okay, so you can see that if you have the the difference between z1 and z2 are the numbers, and you want to find the difference of the between the two. Okay, so z1 minus z2. So this is when you can, this is when you actually use your additive inverse part, okay, that we had just seen in the previous operation. When we were adding, we introduced another term that is called the additive inverse. So you use it when we actually try to find the difference between the two complex numbers. Okay, so then what this becomes is Z1 plus minus Z2. Okay, so let's try the this with the examples that we had taken. Okay, so Z1 is equals to 8 minus 3i, and Z2 is equals to 3 minus I. Okay, and so if we want to find Z1 minus Z2, so what we get is 8 minus 3i. Okay, and we will put the additive inverse. Okay, so additive inverse of Z2 is going to be minus 3 plus I. Okay, so you put the additive inverse directly over here. Okay, since we know Z1 is for the difference Z1 plus minus of Z2. Okay, and then you get this as 8. Again, the same thing, you put the real parts on one side, and then you get the imaginary parts on the other side. Okay, so what you get is 5, and this is plus minus 2i. Okay, and if you simplify further, this is what you get. Okay, so this is how you find the difference of the complex numbers. So if we take another example, okay, so this was A, and then the numbers that we had taken previously, I'll just okay, so we have 6 plus 4i. Okay, so let's try with the Z3 and Z4. Okay, so you have Z3 is equals to 6 plus 4i, and your Z4 is equals to 6. Okay, so if you want to find Z3 minus Z4, okay, so since there is no imaginary part given here, so let us consider that to be 0i. Okay, so this becomes 0 any which way. Okay, so if we get that, so again, this is actually going to be Z3 minus, sorry, Z3 plus the additive inverse of Z4. Okay, so now since we have Z3 over here, so 6 plus 4i, okay, plus additive inverse, so you change the signs, so you get minus 6 over here. Okay, so now over here we can see that the minus 6 and 6 gets cancelled, so what you're left with is 4i. Okay, so this can also be you can try to express it as Z3 minus Z4, 0 plus 4i, or, if you have to write it in the form A plus bi, okay, or you can just keep it as 4i. Okay, so this is how the difference of two complex numbers happen. So let's try to see if the laws that we try to we saw that there were few laws which were being satisfied by the addition of complex numbers. Let's see if the same properties are being satisfied when we try to find difference between two complex numbers. Okay, so for the first law that we had, that was the closure law. Okay, so closure law means that the difference will also be the difference of two complex numbers can has to be a complex number. Okay, so we saw, so that is also valid from the valid from the example that we just saw between Z1 and Z2 and Z3 and Z4. Okay, so this is a complex number, and this is also a complex number. Okay, so closure law is followed. Okay, and the next one that we had seen was the commutative law. Okay, so as per the commutative law that we had seen for the addition, that means the sum of the complex numbers when if you have Z1 and Z2. So in the for the addition part, we had seen that Z1 plus Z2 is equals to Z2 plus Z1. Okay, so no matter how you add the numbers or in which order you write the add the numbers, this was being satisfied. Let's see if the same thing can happen when we are taking a difference. Okay, so we will try to see if Z1 minus Z2 is equals to Z2 minus Z1. Okay, so we are taking Z1 is equals to 8 minus 3i and Z2 is equals to 3 minus I. Okay, so let's first do the LHS part. Z1 minus Z2. So that is equals to 8 minus 3i. Okay, we will directly write it in the form of the additive inverse. Okay, so Z1 plus minus Z2. Okay, so we will write it in this form. Okay, so this is plus and the additive inverse of Z2 will change the signs inside. Okay, plus 1. Now if we take this, so this is 5, 8 minus 3 is 5 and minus 3 plus I will be minus 2i. Okay, now let's see this is the LHS. Now let's see the RHS. Okay, so for RHS we have Z2 minus Z1. Okay, so now that we will write it in the form of Z2 plus minus Z1. Okay, so Z2 is 3 minus I plus the additive inverse of Z1. Okay, so that would be minus 8 plus 3i. Okay, so what we get is now minus 5 plus 2i. Okay, now you will see that the LHS is not equal to RHS, but the LHS, okay, is equal to negative of RHS. Okay, you can see that. So your LHS, okay, if you actually convert this, okay, sorry, your RHS becomes actually negative of LHS. Okay, so you can see over here that if you take out the minus sign over here, so this is minus 2i. Now this is actually your LHS. Okay, so if you now try to see you can see that immediately the commutative law is not followed when we are trying to take a difference between two complex numbers, but you can write it in this form is as Z1 minus Z2 is equals to negative of Z2 minus Z1. Okay, so as you can see over here that LHS actually can become is equal to negative of the RHS. Okay, so we can say that Z1 minus Z2 is actually is equals to negative of the difference of when we change the order of the operators that we are change the order of the complex numbers when we are applying the operator. Okay, so this is how we can see that the commutative law changes, or actually it is not followed directly when we are trying to find the difference of two complex numbers. Let's see if the third law, which was the associative law. Okay, so in the addition part, we saw that the associative law said that Z1 plus Z2 plus Z3 is equals to Z1 plus Z2 plus Z3. Okay, so this is what we had seen for addition. So if we try to find the validity of this law when we are trying to take difference of two complex numbers, okay, so what we will try to see if whether Z1 minus Z2 minus Z3 is actually is equal to Z1 minus Z2 minus Z3. Okay, so I will just write down Z1 we are taking as 8 minus 3i, Z2 is equals to 3 minus I, and Z3 is equals to the example that we had taken, so 6 plus 4i. Okay, suppose these are the three numbers. So first let's find, this is your LHS. LHS side is what we want to find is Z1 minus Z2 minus Z3. Okay, so first we will solve for Z1 minus Z2. So that becomes 8 minus 3i. Okay, so plus the additive inverse of Z2. So change the signs for the Z2. Okay, so what we get is 5 minus 2i. Okay, now we try to subtract Z3 from this. Okay, so now if we take 5 minus 2i, okay, minus Z3, then we write it in the form where Z3 becomes the additive inverse. So 5 minus 2i plus minus Z3. Okay, so Z3, now you change the signs for it. So 5 minus 2i, okay, plus minus 6 minus 4i. Okay, now the real parts and the imaginary parts are equated and evaluated. So what you get is minus 1, okay, and this you get as minus 6i. Okay, so your LHS comes down to, with solving and simplification, is minus 1 minus 6i. Now let's see if we get the same answer if we try to solve the RHS part of the, the statement of the law, associative law. So RHS is equals to Z1 minus Z2 minus Z3. So we will solve this part first for the RHS part, RHS side. So you have Z2 minus Z3. So that becomes Z2 plus minus Z3. Okay, so Z2 is 3 minus I plus the, you change the sign for Z3. So you have minus 6 minus 4i. So what you are left with is minus 3 minus 5i. Okay, so this is what we got. Now, since you can see that actually Z1 is, you subtract Z2 minus Z3 from Z1. Okay, so if you write this as Z1 minus the, what we got for Z2 is actually minus 3 minus 5i. Okay, so now you write this in terms of your additive inverse. Okay, adding the additive inverse of the complex number in brackets. So Z1 plus, you change the signs for the complex number in the brackets, 3 plus 5i. Okay, now what was Z1? Z1 was 8 minus 3i, okay, plus 3 plus 5i. So 8 plus 3 is 11, okay, and this you get as plus 2i. So this is your RHS. So as you can clearly see over here, your LHS is totally not equal to RHS. Okay, so we can say that the associative law is not followed for difference of two complex numbers. Okay, so if we, sorry, okay, so if we see the we can see that the closure law is applied. Okay, so which one is satisfied? We have the closure law that is satisfied, obviously, because the difference between two complex numbers gives you a complex number itself. Okay, so we saw that the closure law is applied. The next one is the commutative law. So commutative law, there is a difference. Okay, so for commutative law, you can see that there is a sign change. Okay, so for commutative law is not satisfied, but we can say that Z1 minus Z2 is actually is equals to negative. Okay, so over here you can see that this actually is the negative of the the answer that we get. Okay, so what we can write is Z1 minus Z2 is actually negative of the Z2 minus Z1. Okay, so this is what we get in place of commutative law instead. Okay, and the next one, the associative law is totally not satisfied. Okay, associative law is not at all satisfied. So we can see that when we are trying to apply different operations on two complex numbers, uh, there is a difference. Not all laws are applicable to both addition and subtraction or difference between two complex numbers. So you have to be careful when you are actually trying to find the difference between two complex numbers. So one important part that we see is that when we are trying to find the difference, you actually add the additive inverse of the second number. Okay, so this is how the difference of the complex numbers can be found easily. Okay, so today we have done two operations that you can have with complex numbers. So one was the addition and the difference. Now, if you want to check the example of another like if we take Z3 and Z4, okay, so if you want to check for your Z3 and Z4, that if let's see if Z3 minus Z4 is actually is equals to Z4 negative of Z4 minus Z3. Okay, so it's like the the what we saw with this. So your Z3 was 6 plus 4i. Okay, so we'll just solve it here and then I can rearrange it. So Z3 is 6 plus 4i. Okay, and Z4 was only 6. So let's find Z3 minus Z4. Okay, so Z3 plus minus Z4. So 6 plus 4i. Okay, and this becomes plus minus 6. So you're left with 4i. Okay, so now let's find Z4 minus Z3. Okay, so this is 6 plus minus 6 minus 4i. Okay, again 6 and minus 6 is cancelled. What you're left with is minus 4i. Okay, so then again you can see that Z3 minus Z4 is equals to negative of Z4 minus Z3. Okay. So if you actually find Z, try to change the sign of this, what you get is 4i. So now it is equal to the Z3 minus Z4. Okay, so we can see that this is also it's an example that you can see that the law holds good. So today we did addition and the difference, the sum and the difference between two complex numbers. In the next class, we will see the product and the division of two complex numbers. We will try to see how like if there are different laws which we will be trying to see, and if they are valid or not valid for both the multiplication and division of complex numbers. So we will end here.